Um, Hi, Parmeet. Am I audible? Can you hear me?
Yes, sir, you are audible.
Okay. Okay, let's start since we're here. And so today is the last session that I'll be taking. And I believe your final exam is next week.
Yes, sir.
So this session I'll be covering the last topic, which is GG1 queues or general queuing systems, which I think is lectures 45 to 48, something like that. Please confirm.
That's 44 and 45.
Okay, yeah, 40 to 43 was last week. So then this is 44 onwards. Okay, so so as I usually do, like for the past few lectures, like I am not fully, I was not fully familiar with the course material myself, so I had to go through the lectures on by Professor Selvaraju. And so I've prepared notes, and I also make them available along with the discussion in the class. So so hopefully this will help. And I plan to solve some problems related to GG1 queues and their distributions. So before jumping to the problems, do you have any particular questions from theory that you would like me to clarify?
No, sir.
Okay, great. So then just give me a minute and I'll start. Okay, so I'll start with actually there are two topics this week actually. The first topic is GG1 queues, where we have the arrival process and the departure process of a queue both having general distribution. So we don't have any idea of how they behave. It's all very general, and hence but using some approximations and some bounds, we do have some idea of what their performances can be given the give, using certain approximations. So we have that, and then we also have the topic of queues with vacations. So GG1 queues with vacations and MM1 queues with vacations and MG1 queues with vacations in general. So uh, so that's another topic. So by queues with vacations, what I mean is that sometimes the server is allowed to go on vacation, that is not serve any user. So then the waiting period of the users, like the users which arrive, the clients which arrive during the vacation period will have to wait until the vacation period has expired. So that is queues with vacations, and so the lecture has enough details on how to analyze that. Um, I won't repeat the theory. I'll just go directly to solve some problems. But in case you have any doubt and you would like me to go over some part of the theory for you, and try my best. Okay. So let's start with a problem on the 1 second. One problem on the GG1Q. GG1Q. Right. So here the arrival and the departure distributions are not known. In general, these are general. These can be anything, but so I can specify anything. So let's say that the inter-arrival times let's denote them as T, are it's actually a fixed value. So I'll just write it as time T is equal to, let's say, some fixed value. Some fixed value 1 by lambda, let's say. Okay. So inter-arrival time is some fixed value 1 by lambda seconds. And then service time S is, let's say, exponential with some value with exponential with parameter mu, right? So something like that. So then the question is, so for the purpose of analysis of GT1 Qs, there is this important variable which we analyze, which is U, which is service time minus the inter-arrival time, which essentially denotes the busy period. And so so the question is, what is the CDF of U? The question is CDF of U as a function of X, right? And we have to find this value out. So what do we mean by CDF of U of X? So this is nothing but U of X. This is some notation that is commonly used in the lecture note. So this is denoted as probability that U is less or equal to X. U is a random variable and the probability that U is less or equal to X is U of X. So we have to find out CDF of U of X, right? So let's figure this out. So U of X is probability that U is less or equal to X, which means this is the probability that S minus T is less or equal to X. Now, we know T has a fixed value, right? T is equal to 1 by lambda. It's deterministic. So essentially, you can write this as something like a D. This example is a DM1Q, right? Because your arrival process is deterministic and the service process is exponential. So it's a DM1Q. That's the example we are taking. So, so the inter-arrival time is 1 by lambda. So this can be written as S less or equal to 1 by lambda plus X, right? Because T is equal to 1 by lambda. Something like that. Right? And then we know that the service time S is distributed as exponential of mu, right? So, so let's find out this integral. So this will be U of X. So S is distributed. So the PDF of S is mu times e to the power minus mu X for X greater than 0, right? That's the PDF, I think. So, so then this will become, it will be an integral of mu e to the power minus mu X dx. Or since the outer variable is X, let's keep the inner variable something like small t dt from 0 to X, right? Let's just also write this as, so this is the so this is the PDF of S, and so I'm integrating the PDF from 0 to, it shouldn't be X actually, but see, this is the probability that S is less or equal to 1 by lambda plus X. So this should be 1 by lambda plus X, right? So yeah, hi.
Sorry to interrupt, but service times are given to follow mean alpha. Instead of mu here, they are using alpha, I think, in the question.
In the assignment, so I am not exactly solving the assignment problems. I'm
Okay.
solving something that's typical. So that's typically what I'll do, because I'm not sure if you have the assignment solutions already, but we have been strictly asked not to solve the exact problems.
Okay.
So I'm trying to solve a similar problem,
Okay, sir.
which will also help. So you will kind of hopefully get the approach right, I guess. So is that okay?
Yes, sir. Yes, sir.
And then you can check that I have switched things up. So the service time here is actually exponential, while the interarrival time is fixed.
Yes, sir.
While in your assignment question, you have it the other way, I believe.
Yes, sir.
So I'm deliberately doing this. This is a different question.
Okay, sir.
You will most likely not get the exact same question as the assignment in your exam, right? You'll get something different. So you should have a general idea. Okay, so this integration is easy to do. This is e to the power minus mu t, right? From 1 by lambda plus x to 0. So then the answer becomes something like, okay, if 1 by lambda is uncomfortable, I can change this to something like alpha. I don't mind, right? So alpha seconds. So then this will become alpha plus x, right? And this is t equal to alpha. And then this integral limits will also change. So it is alpha plus x. And so this is also alpha plus x. So e to the power mu time minus mu times alpha plus x, right? So that's the answer for this problem, right? It's, again, I'm repeating, this is not the solution of the assignment. The assignment question is a little different, but the approach is similar. So the key step here, and here actually there is no restriction on x. X can be any value. So x can be any value greater or equal to 0, right? Or sorry, x can be any value greater or equal to minus alpha. That's the answer, because u is equal to s minus t, and so t is known to be alpha. S is exponential mu, so exponential with parameter mu. So this is, s is greater than 0. So then this is greater or equal to minus alpha. The whole u has to be greater or equal to minus alpha. So that's exactly how it is. Or you can also check from the integral limits that alpha plus x has to be greater or equal to 0, right? So that's how it looks like. So for values x less than equal to less than minus alpha, this should be 1. Let's actually quickly check that. So sorry, this should be 0 for, because because we cannot have any limit below the integral. So, so this should be 0 when x less than minus alpha. So this is solution. Like, is this clear for this problem particularly?
Yes, sir, it is clear to me.
Okay.
So
Okay.
when we solve the integral, we have to put the lower limit as well, na? The integral.
Yes.
When we
Yeah.
put the, Mhm.
Okay. Yeah. Oh, right. You are right. I have made a mistake here. So, 1 second. You are right. So if I integrate this, I'll actually get this thing, right? It will probably be minus a to the power minus mu t. And so, and I've actually missed the lower limit. So it should be,
Yes, sir.
this is correct, right?
Yes,
Okay.
sir.
Yeah. Thank you. This is right. And then, so yeah. So then this will be 0 for
Mhm.
x less than minus alpha. Something was missing. Yeah. This should be correct.
Yes,
This
sir.
should be correct. Yeah. So I missed the lower limit. So the key thing here is, like in this kind of problem, one of the two quantities here is deterministic. So you substitute that value,
Mhm.
and then you use the probability distribution of the other quantity. So in this case, service time had a certain probability distribution. So you use the PDF formula for that distribution, which is exponential in this case. And then do the integration and just be careful when you're solving. So yeah, this is kind of the approach. And so once you have the PDF, you can do a whole variety of things, right? So let's say you want to find out expectation of u, right? So like, actually this is easy. Even without the PDF, expectation of u is nothing but expectation of s minus expectation of t, right? Because u is equal to s minus t. So now we have expectation of t to be alpha because t is a deterministic value, and expectation of s to be exponential mu. So the mean is actually 1 by mu,
1 by
right?
mu.
Right. So then this expectation comes out to be 1 by mu minus alpha. Right. So so yeah, that's all. And then this is one, and another way we can just quickly tally it. Sorry, I made another mistake. I missed the mu factor here. Minus mu into the power alpha plus x. And we can also tally it from this PDF, right? So expectation of u is nothing but, so this is the CDF. And so from one formula for mean is actually this thing, probability u greater or equal to x dx. Let's use y dy y y equal to 0 to infinity, right? Something like minus infinity to infinity. So this is the CCDF. This is one formula of expectation of u. If you are uncomfortable with this, you can simply go to the PDF of u. So if u of x, the PDF will be, we'd have to take a derivative, right? So the derivative of this will be, I think, mu times e to the power mu alpha plus x, right? I hope I'm not wrong. Yeah, mu times e to the power minus alpha plus x is equal to minus alpha, 0 x less than minus alpha. So another way of evaluating expectation of u will be nothing but integral fu of x dx from x equal to minus infinity to infinity. You can use both these formulas and then check if the value that you get is equal to this, because we know the answer. This is the answer. If these values are equal, then your derivation of the CDF and the PDF are correct. Let's quickly actually try the first formula because we have it right here. So u equal to minus infinity to infinity. Probability u greater or equal to y is nothing but the CCDF, right? The complementary CDF. So it is 1 minus the CDF. So this will come out to be e to the power minus mu alpha plus y and then dy. But there was a condition that u has to be greater or equal to y, which means which means y has to be greater or equal to minus alpha, right? Because the smallest value that you can take is clearly minus alpha. So yeah, actually like the smallest value that I can take is minus alpha. So well, I think this is fine.
So we can change the lower limit to minus alpha. Yeah.
I think so. Let me think about it actually. Yeah, probability that u greater or equal to y is 1 minus probability u lesser or equal to y. And for u being lesser or equal to y, yes, yeah, you are this will change to minus alpha. And so this will be 1 by mu minus 1 by mu times e to the power minus mu alpha plus y, right? And then the limits will be infinity and minus alpha. So the upper limit will go to 0, right? Because e to the power minus infinity is 0. Lower limit will come out to be 1 by mu times one second. Yeah. If I substitute minus alpha, it comes out to 1 by mu, right? Then this minus alpha term also has to come from somewhere. So let's try the second approach, which is this one. I think this will be easier to verify. So mu times e to the power minus mu alpha times e to the power minus mu x dx from minus alpha to infinity, right? Yeah, I have to check on this. 1 second. Yeah. Okay, verification. Okay. I'll check on this approach a bit, but like one sure shot way of obtaining expectation of u is definitely this one. I mean, it's easier. So this one I have to check once. But okay. Now So another related question is, let's say we take some values, right? We take the value of alpha equal to something like 3, and then mu is equal to something like half. And we know, and we want to find out the lower limit of the queuing delay.
Yes, sir.
We want to find out the lower limit of the queuing delay. So how do we do that? And let's quickly solve something. So the way it can be verified from the theory is that we have to solve actually this integral equation. So this is the integral equation that we have to solve to obtain this lower bound, like this from the theory. And so we know the value of u of x. So we can essentially, this quantity 1 minus u of x is nothing but the CCDF. And so let's write it down. 1 minus u of x is equal to 1 for x less than minus alpha, and e to the power minus mu times alpha plus x for x greater or equal to minus alpha, right? And so if we solve this equation, what we get is r naught is equal to integral minus r naught to infinity, this thing, right? So integral minus r naught to, let's say, minus alpha, some value minus alpha, we'll get some value minus alpha, we'll get z, we'll get 1 dx plus from minus alpha to infinity, we will get e to the power minus mu times alpha plus x dx. This is assuming r naught is minus r naught is less than minus alpha, right? Or r naught is greater than alpha. So this can be one possible situation, or r naught equal to, again, and if r naught is less than alpha, then this integral will start from this integral will only comprise minus r naught to infinity e to the power minus mu alpha plus x dx. This is r naught less than equal to alpha minus alpha. Oh, sorry, alpha, right? Because this integral, if r naught is less or equal to alpha, that means this integral doesn't exist. It's kind of 0, and like lower limit exceeds upper limit, and so, and here minus alpha is superseded by minus r naught, so we start from minus r naught. So like this, write it more explicitly. Minus r naught is less than minus alpha, and in this case minus r naught is greater or equal to minus alpha. So there can be two possible cases, and let's solve for both. For case 1, for this case, we have r naught equal to minus alpha plus r naught, I think, plus 1 by mu e to the power minus 1 by mu, I think, something like this. And I think this, because this will be 1 minus 1 by mu e to the power minus mu times alpha plus x. and then the upper limit will go to 0, and the lower limit will be the lower limit will be just e to the power 0, which is 1 times 1 by mu. So then this equation leads to R not getting cancelled, so we get something like alpha equal to 1 by mu, which isn't really a solution. So this, we need not have this. So this is a wrong assumption. And so let's try solving this instead. R not equal to 1 by mu e to the power minus mu times alpha minus R naught. Right? Because if we substitute x equal to minus R naught, I think this will be the expression. And so then we can solve this using, like, I really don't know. This is the problem I cooked up. So, and we know the values of mu and alpha. So what were the values that we have taken? Mu is half and alpha is 3, right? So then this will be 2 e to the power minus 3 by 2 minus plus 2 e to the power minus 3 minus R naught by 2, right? And so this has to be solved. And so this, let's draw the graphs just to get an idea. So we have y equal to R naught on the left hand side, and on the right hand side it's e to the power minus something, right? So then it's something like this. So there will be only one unique solution, that is for sure. Now the solution needs to be, so we can solve for R naught numerically. We can use MATLAB or Mathematica or some advanced scientific calculator as well to solve for this and obtain this answer. So there is a numerical solution, and then that numerical solution can be used. So we can obtain that numerical solution basically. And then that is the answer we need, right? We need the lower bound to the queuing delay. Is this clear?
Okay, sir.
Okay. Okay. Right. Now, so this entire thing was one question with various parts you can consider. And now a couple of conceptual questions. So the first conceptual question is, so the distribution of, so let's, the delay that user experiences in the queue or in the line, does it so I want to find out whether this statement is true or false. So the waiting time, is it dependent on both the service time and the inter-arrival time distributions individually? So the answer for this is actually false, because the wait time is something like u of s minus t, right? So it is actually dependent on the difference. So not the exact. So we can have two different situations of FSS and FTT, but maybe the distribution of u for both of those cases is the same, because s minus t somehow turns out to have the same distribution. We can find out, we can cook up some corner cases like this. And so it actually is not dependent on each of these individually, but it's dependent on the distribution of s minus t. So that's why the answer for this is false. And similar conceptual question, like, but this is based on stochastic comparison of variables. So I think I had the theory in here as well, but it's okay. It's even intuitively we can understand. So then, like if we draw a timeline, so there is a point in time at which a customer arrives. There is a point in time at which a customer departs, and then there is a point in time at which the next customer arrives, and the service time starts again, and the service starts again. So we have this interval, which we can call T1, and then we have this interval, which we can call T2. So this is for a GG1Q. Is T1 is T2 stochastically smaller? And the answer for this is actually true. Because it's kind of very evident even from the picture that this time interval between the arrival and the departure, let's mark it as T1 minus T2 for now. So this time interval between the arrival and the departure of a customer has to be positive, right? And so then, like very crudely speaking, T1 is T1 minus T2 plus T2. And so if this quantity is guaranteed to be positive, this will be greater than T2. So T2 is stochastically smaller than T1. So we can kind of argue that like for any value x, so the definition of stochastically smaller is for all x, the probability that T2 is less or equal to x is greater than the probability that T1 is less or equal to x. I believe I got this definition right. So T2 is indeed, and don't need elaborate mathematical arguments for it. It's very even pictorially, it's very evident that the time interval between a departure and the next service time, the next service beginning, is stochastically smaller than the inter-arrival time between two packets. Is this clear? Yeah.
Yes, sir, it is clear.
Okay. So this was a set of problems on GG1Qs. And then we'll be doing some problems on MG1Qs with vacations. Right. So before I start this, is it okay if I take a short break of 5 minutes? I need to attend to something.
Sure, sir.
Okay, so we'll start after 5 minutes.
Okay.
And with this topic, MG1Qs. See you at around 3:45.
Okay, sir.
Okay. Okay. Okay, so I'm back and let's solve some problems on MG1 queues with vacations. And that it from number 4, right? And so the first is a simple question. So we have an MG1 queue, okay, where V of Z is PGF of number of customers in system during vacation, right? So when the server is on vacation, the PGF of the number of customers which are in queue, which are in the system queue and also arrival and departure. So that PGF is denoted by V of Z. And so the question is, what is the so let's say we are observing a queue during a vacation, and so we are trying to observe the residual vacation period, right? As to how much of the vacation period is remaining. And so we want to know, we want to characterize the residual vacation period. So one way of, so we want to know the Laplace transform of this residual vacation period, because this will help us characterize it. And so this is actually derived in the lectures in itself. And so the answer for this, not going into details, it's you can check it. It is derived in my notes somewhere here. So all of these derivations, I have kind of noted them down, but it's better to be followed directly. And so the answer for this actually is given by V of 1 minus S by lambda, right? So this is the PGF of the residual vacation period, and this is the answer. So moving on. Just a second. Okay. So V of C. So let's say for an MG1 queue, this is another problem. Let's say the N star denotes it denotes the number of customers during start of busy period post after a vacation or during the vacation period itself. And let us say we are told that n star is equal to 3, let's say, right? So and so what we want to find out is V of again PGF of number of customers during residual vacation, right? So this is denoted by V of Z. We want to find out this one. And so from the lectures, the formula for V of Z is nothing but 1 minus R of Z by 1 minus Z times expectation of n star. Right, you can just see it from the lectures itself. Not the VS model, it's a VM model. So this is the formula for VZ, right? 1 minus R of Z by 1 minus Z times expectation of n star. And R of Z is the PGF of n star itself. R of Z is the PGF of n star itself, which is the number of customers at start of busy period following the vacation. So then, yeah, so if they are, so R of Z, we know the value of expectation of n star, right? Because n star is equal to 3. So expectation of n star is also equal to 3. That's a fixed deterministic value. Now R of Z is nothing but summation Pn Z to the power P of n star Z to the power n star for n star equal to 0 to infinity, right? And so the only value for which I should write it like, yeah, something like P of n star equal to n Z to the power n. So n star is a deterministic value. So the only probability that, so only P of n star equal to 3 is 1. For all other values, it is 0. So then we can pick out that value, right? So this will basically be 1 times Z to the power 3 plus 0. So this is Z cube. And so we can substitute this here, right? So this answer will be 1 minus Z cube by 1 minus Z times 3. So this is the approach to solve this kind of problem. So this is the PDF of the number of customers which are in the residual vacation period. And any questions with regard to this one?
No, sir, it is clear to me.
Okay. Yeah, so it's just, by and large, most of these questions are just application of formulae from the lecture, right? So let's say now final kind of question, and this is based on, again, MV1 queues with vacations. So let's say we have tennis court, right? I'm just taking an example, and tennis court and let's say there is players arriving arrive in pairs, because in pairs at rate lambda equal to something like 20 per hour or 10 per hour, 10 pairs per hour, right? And then sometimes this is a bit too much, let's say 5 per hour. So sometimes the tennis court needs maintenance, right? So there is a maintenance period. So you know your usual checking the moisture and like laying out the grass and all of that. Maintenance periods are, let's say, exponentially distributed. Maintenance period, let's say some time t. Some time v is distributed exponentially with so the exponential probably is not needed. It's mean is something like 30 minutes, and variance is let's say 5 minutes square, right? So this is how the maintenance period is distributed. It's exponential with this mean and this variance, right? And then exponential, and then it's also told that if the court is empty, it undergoes further maintenance. So if the maintenance period is over and then there are no players when the maintenance period is over, then there is another round of maintenance that always happens for the ground. So that's how this ground operates. And the playing time for players is like, again, the only thing we know about it is that it has mean of, let's say, something like 1 hour, and standard and variance is 10 minutes, let's say, right? So what we want to find out is the mean waiting time in a queue until you get the tennis court free, right? And so how do we compute that? So this is nothing but, the answer for this is an MG1 queue with vacations. This is clear, right? Because the arrival of players is exponential. So we should write it explicitly. This is Poisson. The arrival process is Poisson. So the inter-arrival time is exponential. And then we have the service time is general, so we don't know anything about it. And then we have some vacations which are exponential. So this is an MG1 queue with vacations. And so we have lambda equal to 5 per hour. And then we have expected value of service time, which is the playing time. So the playing is the service being provided, right? This is equal to 60 minutes. And variance is equal to, and so expectation of service time is 1 hour or 60 minutes. And then we also have expectation of vacation is given to be 30 minutes, right? Now, we also need to find out two more quantities here. Because, so we are trying to use this formula. And another important quantity here is, firstly, let us also write down rho, which is nothing but lambda times expectation of S. So we need to be careful about the units here. So this is 5 per hour. So 5 times expectation of, this is also 1 hour. So then I'll actually multiply it with 1, 5 per hour times 1 hour. So then the value of rho is 5, right? And this is the formula that we are trying to use, which is the waiting time in a queue is lambda times expectation of S square divided by 2 times 1 minus rho plus expectation of vacation period squared divided by 2 times expectation of V. This is the formula we are trying to use. Now, expectation of S squared is, as we know, it is usually variance of S plus
S whole square plus expectation of S whole square.
Yes, exactly. And so similarly, we can also compute expectation of V squared equal to variance of V plus expectation of V whole squared. So we can simply plug in those values, right? So lambda is 5 per hour. So let's actually convert all of these values to hours, right? So 5 by 2 times 1 minus rho, which is 1 minus 5 times expectation of S square, which will be variance of S. So variance of S has been given to be 10 minutes square. So we can convert it into hour square, right? So this will be 1 by 36 hours square, right? Because we'll divide by 60 into 60 actually, right? So this will be 1 by 36 plus, this is 1 hour, so 1 square, plus again for V, 30 minutes is half an hour, right? And so this is 2 into half, and expectation of V square is nothing but half whole square, 1 by 4 plus variance of V, which is 5 minutes square, or this is nothing but 1 by 144 hour square, I believe, because we'll be dividing by 1 by 60 times 1 by 60. Sorry, it's even this is actually, sorry, this will be 1 by 60 times 1 by 60. So this is 1 by
360.
360. Yes, 1 by 360 hour square. And so this will be 1 by 1440, right? Hour square. So 1 by 1440 hour square. So we can compute this value. Yeah, we need to check this value. It might come out to be something that is negative. That's what I'm fearing, because in that case, which is great, which means that probably we won't have to wait. But yeah, I didn't choose values carefully. So but this is the approach in general, and in the exam, whatever question you will get, and the paper setter will ensure that the values are chosen correctly.
I think it's a bit calculation error in place of 1440, there should be 720.
Okay.
I think.
Why? 1 second. Oh yeah, 5 minutes square is 5 by 60 into 1 by this, right?
Yes, sir.
Yeah, 1 by 720. You're
Yes.
right. Yeah. So this is 1 by 720. But maybe even then this answer can come out to be negative, I think. It's just my guess. I'm not sure. To compute and see. But yeah, like this is the approach at least. So any situation, it will be like a word problem. And so you have to identify which is the arrival process, which is the service process, which in this case is the playing time. So this is service. This is arrival. And this maintenance period of court, etc. This is vacation. So if you are able to identify and do the computations correctly, you will get your answer. It's a very straightforward, pure formula-based question to answer. Is this okay?
Okay, sir.
Okay. Right. So that's what I had for today. If you have any further questions, I can answer.
No, sir.
Okay. Or in general, any questions other than this lecture also.
Sir,
So
if we are given
yeah.
standard deviation instead of variance, we can calculate the variance just by taking the square of standard deviation.
Yeah, of course. Yeah. So that we know, right? Sigma square is variance.
Yes, sir.
Is variance of V. Yeah, that's those kind of tricks can, I mean, it's not even tricks, you just have to read the question carefully.
Yes.
So that you don't make like silly calculation errors. Yeah. Okay.
Sir, I have still a bit confusion about the bounds. When we calculate the lower bound, we have to solve that integral equation every time.
Yeah, in this, that integral equation has to be solved. Yeah.
Okay, sir.
And so that as shown in that question, right?
Mm-hmm.
Yeah, you have to be careful with the limits and all, but that's the way. And of course, like the exact solution will depend on the question, right? It won't always be same. So for example, I made this change that I made the inter-arrival time constant and the service time was exponential, and then the whole solution changed quite a bit. So, but the more or less the approach remains the same.
Okay, sir.
Okay, like, to know how to proceed. Okay, then. So, so this is all I have. If you have no more questions, you can leave. I'll make these notes available for other students as well and upload this lecture on YouTube. I'll be on call till around 4:30, I think. Maybe if some other student joins, otherwise I'll just cut it.
Okay. Thank you, sir.
Yeah.